Hi, Year 11. Welcome to Week 1, Term 3. I hope you enjoy this term's work, and don't forget you've got the final exam in the last week of this term. And I hope you enjoy Year 11 Engineering Studies and hope you go on to Year 12, which is just as enjoyable, a bit more enjoyable, I think. So let's have a look and see what we're going to do tonight. This week, we're starting another application module, and it's called Braking Systems. And we've done 3 application modules. We've done introductory to engineering studies, and then we've done engineering products, and where we did the lawnmower, and we're doing braking systems now. And then towards the end of this term, we'll be doing a focus module, which is biomedical engineering, which I hope you'll enjoy. So this is straight from Moodle, but it's been changed and I haven't bothered to change it for this lesson. Number 2 here, please print the braking system module notes. Now, you don't have to do that, of course, because you've already got the module book that I've included in the package, so you don't have to print off the module notes. And I'll go through a question that has given some of you a bit of pain on the 3/4 rule and moments, and then we'll just do another moments question, and then I'll introduce you to braking systems, and hopefully you enjoy this module. So let's have a look at this question here. This is a question that puts everything together of what we've learned in mechanics in terms 1 and 2. So here you have a lever and it's pivoted there, and you've got a switch rod here, and it's a sort of a micro switch there, and you're applying a force at an angle at 35 degrees and a force of 10 newtons. The question asks you to find the force in the switch rod when a force of 10 newtons operates as shown. So you've got to find the force in that switch rod. Then the next question, you've got to find the stress in the switch rod. Now, make sure you know the difference between force and stress. And then the most difficult part is you've got to find the reaction force at the pivot when the 10 Newton force operates as shown there. I'm going to show you 2 ways of doing this, and the easiest way, I feel, is using the 3/4 rule. And so I'll just go through the 3/4 rule and explain it, and then I'll show you how to do it using analytical mathematics. So the 3/4 rule says that if 3 forces are acting on a body and a body is in equilibrium, the 3 forces will all pass through the same point. So if I'll just get a line here. So if I extend this force up there along its line of action, and this force along its line of action, where they join, that's the point of concurrence. And we know straight away that the force that's going through this point here has to go through the point of concurrence by the 3/4 rule. So you just draw that through there, and there we have the free body diagram. Now, don't forget, this is not a mathematical diagram. All it's doing is showing you the direction of the forces, not the senses, but the direction. Remember, direction is shown by the angle off the horizontal. So this force here is vertical. We don't know if it's vertical up or down, but I mean, if this force is trying to rotate it clockwise, this one will have to rotate it anti-clockwise, and we don't know So this force here will be going up, but we don't know whether that force is going up or down. And you don't have to, because the 3/4 rule will tell you. So the next thing you do is you use Bose notation, and I've used Bose notation here. You put a capital letter between the forces, so A is all the way around here, B is there, and C is there. So that means that this force here is CA. This force here is AB, and this force here is BC. You've always got to read Bose notation clockwise. The next thing that you do is to work out a scale, because we're going to do this using graphical methods. And in the exam, you're given 10% leeway. So if the answer is 100 newtons, we will accept 95 to 105 newtons. But if you do it analytically, like this method down here, you'll have to get 100 newtons to get full marks. Now, the idea, and I've told you this previously, to get a good size force diagram, you go to the biggest value, and it's 10 here, and you make that equal to between 30 and 100 millimeters. And so I've set up a scale here. 10 newtons equals 50 millimeters, so 1 newton equals 5 millimeters. And so the next thing you do, and I'll use a different color here for the force diagram. I'll use green. The first thing you do is to draw in the force that you know. And so I'd always start from the point of concurrence. And so you draw that there, that force, put the sense, that's not a very good color. And that force is CA. So you just mark it as CA, not a good color. And you've drawn that 50 millimeters long. Now the next force that you come to going clockwise is AB, and you've already got A there, and so you just draw a line either straight up or straight down, because we don't know whether that's going up or down, but you can see that it's got to be going up. And that's as far as we can go with that, because we don't know what the magnitude of that force is. So the next force that you come to, going clockwise, is BC. And we've already got C there. So all you have to do is draw a line through C parallel to that line. And you know how to do that with your set squares. So you just draw a line parallel to that with your set squares, and there is your force diagram. Now see this sense here, that tells you that this goes up and that one goes down, that force goes down. And I'll get a better color, I'll get red. And so straight away, you know that force goes in that direction, and so this force has to go in that direction, and that force has to go in that direction. Actually, these are senses, they're not directions, because the whole thing's in equilibrium. And because this is a mathematical diagram, it's a mathematical diagram because of the scale, we can just measure off this distance there, and you've immediately got the force in the pivot. You measure off this distance here, and you've immediately got the force in the switch rod. And so I've done that. So AB, and this is AB there, that distance there is 74 millimeters. 74 divided by 5 is equal to 14.8 newtons. So that's how you do this first question. But we've answered this question as well, because we know what the magnitude of that is. So let's go down to number 3 here. BC is 110. That's BC there. It's 110. Divide by 5, which gives you 22. You just measure that angle with the protractor and you put it in. You say the point of application is the pivot, right? The pivot there, and you're given the sense. And so you've answered 2/3 of this question from one diagram. Once you've found the force in the switch rod, you know how to find the stress. The stress is the force per unit area, right? Stress is force, that's per area. And so put your information down here. So the force is 14.8 newtons. The cross-sectional area, you're given, it's 5.4. So it's pi r squared. Got to multiply by 10 to the minus 6 to bring it to meters squared. I don't put 10 to the minus 6 here because I call the answer megapascals, and so you've got 1.18 megapascals. Let's go down and have a look and see how you do it analytically. So to do number 1, and I haven't set this out correctly, not like that there, because this is for teachers, not for students. So the sum of the moments about the pivot equals 0 with clockwise positive. So I've converted that force to a horizontal component, which will be cos, 10 cos 35. So that's 10 cos 35 multiplied by the perpendicular distance of that component, which is 63, minus, now I haven't considered the vertical component of this 10 Newton force here, because by the principle of transmissibility, that goes straight through the pivot point, and so does not create a moment because there's no distance between the force and the pivot point. So you don't consider the vertical component of that 10 Newton force. Minus F times 35, we've called the force in the switch rod F, multiplied by the perpendicular distance 35, and you get 14.7. So almost the same as that. Okay, so that's how you get A analytically, B, number 2, I mean, we've done that. Now, to get 3, the reaction force, you've got to say sum of the vertical forces equals 0 with up positive. And so you've got 10 sine 35, which is a vertical component of the 10 there, plus this 14.7 going up there, and plus the vertical component at this pivot here, which I've called Fy because y is going up, and P for pivot. So I've got FYP plus 10 sine 35 plus 14.7 equals 0. So I get the vertical component of the reaction force at the pivot to be 20.44. Then I say the sum of the forces in the x direction at P equals 0, and right is positive. So I've got the horizontal component at P, which is Fxp, which I'm saying is going in that direction, going to the right because it's positive, right, because right is positive, plus 10 cos 35, which is the horizontal component going in that direction, minus, equals 0, right, because there's no horizontal component with that force there. So therefore, Fxp equals minus 8.19. And so that minus tells me that that's wrong. It's going in the other direction. Okay, so, and so you use Pythagoras. So the square of that plus the square of that is equal to the square of the force BC. So I've squared it there and I've got 22 newtons. And then you say tan theta is equal to opposite over adjacent, which is 20.44, that, divided by 8.19, which is that, and that will give you the angle or the direction, and you just say it's down to the left. Okay, so that's how you do it mathematically, but it's much easier to do it using the 3/4 rule, I think. Okay, what I'd like you to do now, as a bit of practice, I'd like you to have a look at this question, and I'd like you to pause the recording now and do that question. You should be able to do that now. So pause the recording and do it, and then I'll go over the solution. Okay, hope you all got it. I hope you've got 18.3. This is how you do it. Sum of the moments about A equals 0 with clockwise positive. So you've got 10 multiplied by the perpendicular distance of that force about that point. And look what they do. They make you add that to give you 1.3. If you just took 10 times 700 or 0.7, you'd be wrong. It's got to go right back to the pivot point. And that's going anti-clockwise, because I've said clockwise is positive. Minus F, that's going anti-clockwise as well, multiplied by 0.6, because we're using meters. Plus, this is going clockwise, 40 times 0.6. Make sure this is kilonewtons and that's kilonewtons, so your answer will be in kilonewtons. Then you don't put all that in your calculator. You put it down like this here. Then you work out what that is and you put it there. You work out what that is, you put it there, and you can just transpose that 0.6 to be the denominator. But whatever you do, don't miss that step, because so many people just try to put that in brackets in your calculator, and it generally ends in disaster. And so the answer is 18.33 kilonewtons. I hope you all got that. What I'd like to do now is just introduce you to brakes and braking systems. And this is in your engineering studies module book, and I'll just go through this fairly quickly. And if you have any problems, just call me or email me. So here's the historical background for braking systems. The idea of the braking system is to slow something down. And in other words, you're converting kinetic energy into heat energy, basically. And the heat energy has to be dissipated. Now, this early brake here, this is an ancient cart brake, and it's not actually a brake, it's just a mechanical lock where you put a hole in the wheel and then you put a stick through there, and it's just like a parking brake. So you can't apply that gradually like these other brakes. These Roman chariots use a servoing effect. Now, servoing means that the motion of the object tends to bind itself on. Now, you know, when I guess you've tied a boat up to a wharf, and the more times you wrap the rope around the pier, the less force you have to hold. And that's because of the servoing effect. As the boat is pulling on the rope, it's putting a normal force on the rope and increasing the coefficient of friction. And that's called a servoing effect. So the more the force is pulled on the rope, the tighter it will bind and it will hold the object much more firmly because of the coefficient of friction. And so all these Roman chariot riders used to do is they used to pull on this, and it would pull the chain tighter around the axle, and by a servoing effect it would stop the wheel from spinning or slow it down, the more force he puts there. Then with these carts, an old lever brake was developed, and this just uses a lever. So you can see the lever arm there is small, and the lever arm there is large. Lever arm there is small, the lever arm, and the lever arm here is large. So the fellow pushes that forward, and there's a big lever arm there compared to there, so that's going to create a big force along here, and you've got a big lever arm creating, it has to move a lot further, but it creates a high force on there. But all that's doing is just by friction, just stopping the wheel from turning without any servoing effect, not like this here. Then band brakes were used because these sorts of brakes were subject to all the muck on the road. So when it goes through mud, it used to, and dirt and stones, the stones would come up and create havoc on the brake lining and wear the brake lining out fairly quickly. These brake linings were generally made of wood or leather linings. Sometimes they used rubber when rubber was developed, or they also used to pack them with horsehair, which increased the coefficient of friction. Then they developed band brakes to try to get the brake out of the muck. And so these band brakes were generally inboard, so they weren't subject to all of the dirt and grime that the wheels are going through. And these are used now on parking brakes on trucks, and more importantly, on bands in automatic transmission, so that when you take off in first, the first band is tightened on first gear, and it's tightened by an electronic solenoid. It's worked by the ECU of the car, the electronic control unit. And then when it gets up to a certain speed, the ECU releases this solenoid and immediately connects the solenoid to the second gear band. And that's how the band brakes work. And this is a band brake from an automatic transmission. Then they tried to get the brakes away from all the dirt and the muck. So they developed these brakes here, which are called drum brakes. And Louis Renault developed these in 1902. And the major reasons for these drum brakes is, one, to get the brakes away from all of the dirt on the roads, because as you can imagine, all the roads in the early 1900s were mainly dirt. And the second thing is that Dunlop developed a pneumatic tyre. And so you couldn't use the rim of the wheel any longer because it's a pneumatic tyre. And so they developed this drum brake. And it protected the linings against weather, dirt, and dust. And this is what a drum brake looks like. Drum brakes are generally on the rear of cars, and they're fairly cheap cars. If you buy a reasonably expensive car, they've all got disc brakes. But I think if you pay 18, 20 grand for a brand new car like a Hyundai i20, you'll have drum brakes on the back. And drum brakes are fine, but they're nowhere near as efficient as disc brakes that we'll have a look at later on. Now, the early drum brakes were mechanical. Can you see this? This is a mechanical lever. There's no hydraulics or no electronics in it. All it is, you pull that lever, and this is subject to rusting and everything. And then this cam turns around, opens up these two brake linings and pushes them against the brake drum, and that's what slows it down. And when I was your age, we had drum brakes on our cars, and these were very dangerous because you had an unequal force on each wheel because of this rusting of the cables and this mechanical setup. And you'd put your brakes on, and you'd very rarely pull up in a straight line because of the unequal force on the wheels. And this was fixed by hydraulic brakes because remember, the hydraulics principle is Pascal's principle of force is evenly distributed throughout a fluid, a liquid. And so hydraulic systems were much more efficient and they provided a much more even force to wheels. They require less maintenance because there's none of these linkages that existed on the mechanical brakes. And the good thing about hydraulic brakes is that you can arrange them to be self-servoing. And so this is the old style hydraulic brakes. You had a hydraulic cylinder there, and all it did, and these were connected to the backing plate so they wouldn't slide. And all it did when you put your foot on the brake, it pushes a piston out and pushes the brake lining up against the brake drum. But this is the latest thing with brake drums. Like these Hyundais would have this servoing effect. So what they've got down here is that you've got floating brake shoes, and they're just connected roughly there, and you can move these up and down so that when you put your foot on the brake, this lining goes out, and if the brake is going in this direction, it tends to drag the lining around. And as it's dragging the lining around, it's forcing this one up against the brake drum. And that's called self-servoing. And so you don't need a great deal of force on the brake pedal to operate these because they're self-servoing. The brake linings pull themselves onto the brake drum, and that's called self-servoing. So a modern hydraulic drum brake with two leading shoes, they call them leading shoes, even though this would be a leading shoe because it's going in that direction, this becomes a leading shoe too because when this is pulled on, because these are flexible, it pushes that on to the other side, and they're both called leading shoes. And it creates a much better servoing action. So that's drum brakes. And the lining material, asbestos, was developed in 1908 by Herbert Froude, and he founded this Ferodo company. You may have heard about it. And asbestos was great for coefficient of friction of 0.35 to 0.2, and had great wearing qualities and great heat dissipating qualities. But it killed people by creating a cancerous growth in their lungs. And so it was banned in 2003. So most brake linings now are very secretive. The compositions are very secretive, and they're made from a combination of ceramics, carbon, and Kevlar fibers and other polymers, generally in a matrix of epoxy resins and other sorts of resins. And so we go on to disc brakes now, and disc brakes are far more efficient than drum brakes. And the problem is with disc brakes is that you need a tremendous force to push those two little pads together on the disc. So this is what a disc, or that's called the rotor, and you can see those holes in there. The more surface area you have on the rotor, the more heat they can dissipate. This is what a disc brake looks like. If you've never seen one, look through the wheels of a car and check out a disc brake. So there's the rotor there, and this part here is the caliper. And modern trains are using disc brakes now. They couldn't use them before. They used to use lever brakes, but now with the technology of the brake lining material, they can use the disc brakes. So these are the parts of a disc brake. So there you've got the rotor, or the disc, and this is called a ventilated disc, where you've got holes up the center, and this is the caliper. And the caliper is called a floating caliper. So you've got a piston on one side, and you've got the caliper with the linings, the brake pads, on either side of it. And so when you put your foot on the brake, it forces this pad up against the rotor, and then the caliper will float back and push that pad on the rotor, and that's called a floating caliper. The discs are generally made from grey cast iron because of the graphite in the disc. It's a good wearing quality, and it's easy to machine, and it has great heat dissipation. And the caliper is generally made from aluminium alloy because you want it to be light, because you don't want heavy brakes on a car because it affects the shocks of them. Now, remember I told you that the major disadvantage with a disc brake is that the average human leg can't put enough force on these two pads to stop the car. Now, if you want to prove that and make sure you do it safely, just leave the engine off your car and roll down the drive. Make sure you got your handbrake ready, and try to use your foot brake. You'll have to press very hard to pull the car up. So what they've done, what the manufacturers have done, they've provided the car with a brake booster. And this is how it works. You've got a valve here which is connected to your inlet manifold. Now, as you know, when you've got air rushing at a high speed, by Bernoulli's theory, which we'll be doing when we're doing aeronautical engineering, the higher the speed, the lower the pressure. And the lower the pressure, the higher the speed. So that if you've got air rushing in your inlet manifold, which you have, to get an air-fuel mixture exploding in the combustion chamber, the air is rushing in at high speed, so therefore you've got a low pressure there. So that when you put your foot on the brake, it opens up this valve to the low pressure area of your inlet manifold, and you've got a big diaphragm, which is spring loaded. And as you suck the air out of here, it pulls the diaphragm along, and your diaphragm is connected to the shaft in your master cylinder. So the more you put your foot on the brake, the more this valve opens and the more assistance you get with your brakes. And this is called a brake booster. And I'll show you what a brake booster looks like. Have a look at it underneath the bonnet of your car, or your dad's car, or your mother's car. So this is the engine here, and that is the inlet manifold. And see this here, see that line going across there? That's connected to your inlet manifold. So the air is rushing into your engine there, creating a low pressure. And as soon as you open up, put your foot on the brake, you'll open up this valve and see this big vacuum chamber here. That's the diaphragm. As soon as you open up this side becomes evacuated of air, and it pulls the shaft through into your master cylinder. Now this is your brake fluid here, and it will pull the shaft along and help you put your brakes on. Okay, and this is your hydraulic cylinder here, and that's where all the hydraulic fluid is when you top up your brakes. So that's what a brake booster is, and you need a brake booster because disc brakes need a lot of force to put on. Drum brakes don't, because they're self-energizing with the two leading shoes, as I mentioned before. Okay, I hope you understand that, and I'll speak to you later. Thanks, bye.